Test on Zoom. Can you hear me real quick? Just give a thumbs up in chat or just say something.
Hi, everybody. Hello. Thank you all for coming. We're going to start probably in about 2 minutes or so. We're just getting some stuff set up. But thank you guys all for coming. Hope you're all interested to learn a little bit about quantum computing. And yeah, we'll just start in a couple minutes. All right. Thank you. All right, we're going to get started. So how's everybody doing today? You guys had a good long day? I don't know. So yeah, thumbs up. I'm seeing some thumbs up. Nice. All right. So this is the quantum computing triple play presented by the UT Quantum Collective. So we're an org dedicated to undergraduate, graduate, and postgraduate students interested in quantum computing. We organize social events and stuff. We'll have a slide up there just to talk about ourselves. But this event is meant to be a little bit of outreach for people who are at any level of quantum computing, just to get a little more familiar with it. So we can get started. Nice. So this is today's agenda. We'll start off with our welcoming remarks right now. And then right after, we'll have Scott Aaronson talking about the history of quantum computing since Democritus, Denise Ruffner, who will be talking about quantum hardware research and industry, and Whurley, that's short for William Hurley, CEO of Strangeworks, who will be talking about software making quantum computing accessible to everybody across the world. So, and then after that, we'll have refreshments and networking. At any time, if you guys are thirsty or hungry, there are cookies and sodas at the back, along with plates and napkins, and there'll be pizzas arriving later. So you can go up at any time and grab some food. That's all free, of course. Yeah, we're not charging. Next slide. Yeah, so a little bit about this event. We were very impressed by the RSVPs we got on Eventbrite. As you can see, we have people from all around the world, every single continent except Antarctica. Unfortunately, we couldn't get any penguins to RSVP, but we tried our best. Yeah, and then the next slide. Yep, so this is a breakdown. I don't know if you guys remember, but when you RSVP'd, you expressed what level of quantum computing experience you have. And so this is a breakdown across all the different categories. Of course, we've got the most for people who are quantum curious, just getting introduced to quantum computing. But across the rest of them, it's a pretty even split. So we're very pleased to see that. And so we have a very diverse audience today. Yeah, next slide. Oh, and note that population size of 679. That's pretty big. Anyway, thanks to all of our sponsors and supporters for making this happen. So Atom Computing, Strangeworks, QSecure, Quantum Computing Report, the Quantum Curious, and the Quantum Information Center at UT Austin. So yeah, all of our sponsors were very instrumental in making this event happen. And yeah. We also have a number of collaborators. So you can take a look at the slide if you'd like to see them. But all of these people people in organizations were very helpful in getting this event off the ground. Yeah. Next slide. Yep. All right, and this is a little slide about the UT Quantum Collective. So we're an org at UT Austin dedicated to helping students like you get interested in quantum computing. We run hackathons every fall, directed research reading programs every week or so for beginners and also intermediates. We have learning labs, which help you get certified through the IBM Qiskit certification process. So that'll work through the IBM textbook on quantum computing. And we also have guest speaker events like this one today. So all of that and more you can get access to through our Discord. So we'll leave this slide up at the end of the event, but if you guys want to scan that and join our Discord and get involved, that'd be great. Yeah. So without further ado, let's introduce Scott Aaronson and then we'll get going.
So, hey guys. First up is going to be Dr. Scott Aaronson, who is the David J. Bruton Centennial Professor of Computer Science at the University of Texas at Austin, and also the Director of its quantum information center. In addition to making foundational contributions to quantum complexity theory, Dr. Aronson keeps the public honestly informed about what quantum computing can and can't do through his popular blog, Shuttle Optimize. He is also the author of Quantum Computing Since Democritus, which you have all received a link to, in which he takes a Socratic tour through some of the deepest ideas in math, computer science, and physics. So without further ado, Dr. Scott Aronson.
All right, can you hear? So, hi everyone. So, and welcome here. So, I should say I had nothing to do with organizing this event, but my purpose here is, well, first of all, to thank the people who did organize it. It is great to see more quantum activity at UT, and especially, the students who are part of this quantum collective and who are putting on events like this one. So, so we have a small but growing quantum information center here at UT, which is between computer science, where I live, and physics and ECE, electrical and computer engineering. And we're hoping to get maybe math and chemistry involved too. But we've got a few faculty. We've got a great group of postdocs and grad students, undergrads. We have affiliated people at the Texas Advanced Computing Center and the Applied Research Lab in North Austin. So, Austin has become more and more of a startup hub. There's people are moving from Silicon Valley to here more than the reverse. And we do now have some quantum computing startups, such as Strangeworks, and you will be hearing about that later. So what I thought that I would do, both because it's the easiest and because it's the most fun, is just take questions. So I am happy to field whatever is on anyone's mind about, the theory of quantum computing, about the quantum computing industry, about quantum algorithms. I may not know the answer, but I can at least spout about just about anything. So so I'm happy to talk about whatever people would like me to. All right. You want to? Well, okay. I mean, there are a bunch of approaches, being pursued to hardware implementation of quantum computing, and you're going to hear about some of them. There is superconducting qubits, which was what, for example, Google used for its quantum supremacy experiment in 2019. There's photonic qubits, okay, which is what's used for boson sampling, for example. That was the other route that was taken to demonstrate quantum supremacy over the past couple of years. In that case, by the group of Chaoyang Liu and Jianwei Pan in USTC in China. Optical qubits are also being used by the startup PsiQuantum in Palo Alto, which PsiQuantum. It's a startup company. They've raised about $1 billion in venture capital to try to do this, and they have 100 people. So that might or might not succeed. But okay, there is trapped ion qubits, which is being pursued by, for example, IonQ. Okay, which actually just went public recently. There's topological qubits, which is being pursued by Microsoft, and they've Microsoft has placed a huge bet on that. And there are yet other approaches like cold atoms, silicon dots. Okay, now the fact that there is this variety, this whole zoo of different approaches. On the one hand, it's great that we have all these ideas to explore. On the other hand, you should be worried about it, right? Because this is not how classical computing has worked, right? Classical computing, there was, there were a bunch of ideas in the early days of, how would you actually build a scalable classical computer? But then eventually, one technology came to the fore, namely the integrated circuit, made of transistors, made of silicon transistors, and it just destroyed everything else. Okay, it was just so much better than any competitor that it just became the thing that we all rely on. And what a lot of people would like to know today is, well, what is the transistor of quantum computing, right? And I think it's fair to say that if that exists, then it hasn't been built yet, and we might not even know what it is. I mean, if you talk to the partisans of any of these hardware approaches, or at least when I talk to them, while I'm talking to them, they'll have me completely convinced that their way is the only way to scale and that no one else has any idea what they're doing. The trouble is that then the next day I'll talk to a partisan of a different approach, and they'll have me equally convinced. Okay, so the trouble is, like theory cannot resolve this question of like which is the which is the right hardware approach or the right combination of approaches. I mean, it can inform the discussion, but you can say all of these approaches are trying to get to the same place, right? They're all trying to get to a universal set of operations on qubits. That then if and when they succeed, then kind of the result is the same with any of them, right? It's a programmable universal quantum computer. The trouble is that we are just in this technological epoch right now where we can't yet get there, right? And because we're in that, we are temporarily, I guess, stymied in trying to build a scalable, fault-tolerant quantum computer. Then the question becomes one of, well, what can you do with kind of the noisy hardware that we've got today, the more limited hardware, where maybe we can only do 50 to 100 qubits, maybe we can only do 1,000 operations on them, 1,000 gates, maybe we can only do a limited, non-universal set of operations, and then the differences between all these hardware approaches do become relevant. Okay, but if some people hope that topological quantum computing will have a sort of natural error correction built into it. And if so, that could sort of serve as the transistor of quantum computing. But so far, not even a single qubit has been demonstrated by that route. Microsoft is working on it. They claim to be making progress. But right now we're at 0 qubits by that approach compared to, let's say, 50 qubits by the superconducting or trapped ion approaches. Okay, so yeah, another question. Yeah. Yeah, okay, that's a good question. You could say ultimately the only benchmark that we care about is like what interesting problems can you solve with this device? Okay, and what problems can you solve with this device that a classical computer would not have been able to easily solve, right? So you could say, that is the ultimate benchmark, right? All other benchmarks derive their legitimacy from that benchmark, right? They are only interesting insofar as we think they're telling us something about that benchmark, right? And I emphasize this point because, people have come up with benchmarks. I mean, a few years ago, IBM came up with this thing that they called quantum volume, right? Which is, one way to try to measure, where, I mean, what's good about it is, you don't want to just ask how many qubits do you have, okay? Because then someone will come along and they'll have, 100,000 qubits, but they can't control them. They can't put them into the superposition states that we want. And in that case, well, who cares how many you have, right? Someone else will say, well, we can keep our qubits coherent for an entire day. Okay, but that's only if nothing is being done to them, right? And they're perfectly isolated in this nitrogen vacancy center or whatever. Okay, and so then again, who cares how long it's coherent if you can't operate on it, right? So quantum volume was one attempt to try to combine together all the different desiderata that you need. Like you need a lot of qubits, you need high connectivity, you need them to maintain their coherence, over like a computation of a reasonable depth, right? And then, so you can invent one metric that kind of puts together all of those things, and that's an improvement over just the most naive thing of like asking someone how many qubits do they have, right? But I have to say that I do worry about Goodhart's law. Goodhart's law? It says that like as soon as any metric becomes a thing that is optimized on, then it ceases to be a good metric, right? So, this is a very, very common thing, right? That like as soon as you say, well, here's my numerical score for goodness of quantum computer, then you just incentivize, all the experimental groups to do like whatever uninteresting hack they possibly can to just increase that measure, right? And so I am not going to cede my judgment to any one of these measures, right? And when any experimental group, has a new announcement to make about what they built, basically, I just want to, I want to hear all the details about it openly, right? And, so one metric that I care about is, have they actually released a paper? Do they have a paper on the archive where I can see all the technical specs of their new device? Or is this just a press release, and a website where I have to try to work backwards, from all this marketing ease and try to infer what they actually did on the actual engineering level, right? What? The archive is the repository of all the quantum computing papers. So yeah, so if you don't know about that, then that would be the very first thing, the arxiv.org. That is where basically all math and physics and computer science papers go or have gone for the past 30 years. That's where you find the literature of quantum computing. That's like, so again, when someone, if someone puts like a web page with a lot of pictures, right, like they're aiming at, investors or at journalists, right? But if they put a paper on the archive, that is when they are talking to other experts, right? And, in general, if someone is only talking to the public and they are not trying to bypass, they're trying to not talk to the experts who could evaluate their claims, then, in quantum computing, just like with everywhere else, that is a red flag, right? Yeah, yeah. Oh, all right, fine. Mm-hmm. All right, so let's back up a little bit. So NISQ is an acronym that stands for Noisy Intermediate Scale Quantum. So this acronym was coined by the physicist John Preskill maybe 5 years ago, and he was trying to refer to, let's say, the current era in quantum computing, namely the era before we have fully scalable and fully error-corrected devices. Okay, so as I was talking about before, we are now, and maybe, for, at least, I don't know how many more years, but for, at least, some more years, we will be in an era where we cannot yet build, a fully error-corrected quantum computer. Like, we don't have qubits that behave perfectly, that we can just scale to as many of them as we want. We will have noisy qubits that you could only do some limited number of operations on before they lose their quantum coherence, before they lose their superposition nature, and and we will be inherently very, very limited in what we can do with them. Okay, so the first really, really important thing for all of you to understand is that as far as we know today, as far as we can figure out, there might be no applications of quantum computing in the NISQ era. Okay, this goes against 1,000, like almost every marketing thing that you will see. As someone who works in this field, I am telling you that it is nevertheless true. Okay, so we will be lucky if we will be able to get any advantage with a NISQ device for any useful problem. Okay, we don't yet know how to do it. Okay, so there are a whole bunch of algorithms that people publish about that you could implement in the NISQ era, like this QAOA, which is this optimization method, a whole bunch of things for machine learning, for generative modeling. The one question that you have to ask about every single one of these things is, does it outperform a classical computer? Okay, and if the paper does not address the question of does it outperform a classical computer, then assume that the answer is no. Okay, because if the answer was yes, they would have said so, right? There is, I would say this is like the problem of quantum computing, of quantum computing research, right? That it's never enough to just do something with a quantum computer. You have to beat what a classical computer could do. right? That is when it becomes interesting, okay? And, you know, as simple as it sounds, right, you can go, you know, on the archive, for example, you can find thousands of papers about quantum algorithms that will like investigate all different aspects of them and then just either just not address at all, like how does this compare to the best classical algorithm? Or else they'll say, well, that's just a question for the future, right? You know, we can't answer that. That's too hard. Okay, so I think that the best bet for getting a speed up in the, you know, for getting a speed up for a useful problem in the NISQ era is probably some form of quantum simulation. Okay, if it can be done at all, I think that our best bet is, you know, to learn something new about condensed matter physics, you know, about solid state systems, about high temperature superconductors, maybe even about, you know, models of quantum gravity, conceivably even about chemistry. Okay, in these cases, you know, we have examples where at least the number of qubits looks very favorable. With you know, 100 to 200 qubits, you could already start learning new things about these you know, interesting quantum systems. Some of which are scientifically interesting, some of which are even, you know, commercially relevant, or, you know, relevant to drug design or materials design or other practical areas. Okay, the big problem that we still have with that is that, you know, all of these quantum simulation algorithms, they seem to require a circuit depth that is in, you know, the millions. Okay, or you know, and we can't do that now. Okay, without error correction, you can, you know, what people can do today is they can do maybe a depth of 25, you know, like 25 layers of operations. Okay, this is why error correction is so important. This is why error correction is the big prize that all of the, you know, Google and IBM and Microsoft and Amazon and, you know, all of the others, you know, and PsiQuantum and IonQ and all the others who are pursuing this are now racing toward. Okay, once you get error correction, then you're no longer limited in depth. Okay, but before you have error correction, you know, if you can eke out an advantage for a useful problem, then it will have to be via a circuit of a very small depth. You know, it is possible that you will do something interesting for quantum simulation, for example, but we don't yet know how. You know, if we do get an advantage, you know, it is likely that like we will first see advantages that are scientifically interesting, you know, that tell physicists or, you know, chemists something that they didn't already know. That might come before we see advantages that are commercially interesting, right? Which is, you know, maybe a harder requirement. Okay, but, you know, ironically, you know, some of the very first things you might be able to do is just simulate models in theoretical physics, including like models of black hole evaporation or the early universe and things like that, that would then tell physicists in the relevant areas interesting new things. So I'm cautiously optimistic that, you know, we will be able to see near-term quantum computers used for that kind of thing. And, you know, then the other thing, the other place where I would say we have a shot with near-term quantum computers is for sort of various cryptographic problems, where we get to sort of design the problem however we want, you know, as long as it is classically hard in the appropriate ways. So, for example, you could imagine using a quantum computer to generate certified random numbers. Okay, now, of course, you know, it's very easy to, you know, there are lots of ways to generate random numbers, right? You don't need a quantum computer for that. Okay, but what's harder is if you want to generate random bits and then prove to anyone over the internet that you really generated these randomly. Okay, that is something that is needed, for example, if you want proof of stake cryptocurrencies. You know, if you want something like, you know, that gets the advantages of Bitcoin, but without like wasting a good fraction of all the world's electricity on, you know, inverting a hash function, right? Proof of stake. So for proof of stake, you need to constantly run a lottery to decide who gets to add the next block to the blockchain. Okay, so you need some source of randomness that everybody trusts. Now, you know, a near-term quantum computer, you know, as I and others sort of observed, you know, 4 years ago, could already be used for that, except that we don't have a fast enough way to verify what the quantum computer is doing. Okay, but if someone manages to discover that, then that could be an application of quantum computing that you could maybe already realize today. So, you know, now in addition to that, people are going to try these quantum algorithms for machine learning and for optimization with near-term devices. I mean, one company, D-Wave, has been doing that for a while, right? I guarantee you that no matter what the results, they will be saying that it's revolutionary and that it enables all these new applications. Okay, the question you're always going to have to ask is, what if you compare against the best classical optimization heuristics, right? Because so far, when we've done a fair comparison, we haven't seen a win there. But partly the question is experimental. People are going to have to try these algorithms out, on near-term quantum computers and try, as hard as they can to honestly evaluate their performance in practice, against the best classical heuristics like simulated annealing and so forth. So I hope that, if nothing else, we're going to be able to learn a lot about the performance of these quantum algorithms by trying them out on these devices over the next decade. I hope that, yeah. Yeah, so, okay, so there are, okay, all right. The question was, what kind of software startups are there in quantum computing? If you go back, like, let's say 6 years, 6 or 7 years, there was one quantum computing startup, right? That was D-Wave, which was, out there sort of, saying things that, some of us had some issues with, okay? Nowadays, it's a completely different landscape. There's more than 100 quantum computing startups today, like working on sort of every different aspect that you could imagine, right? Some of them are actually building hardware, IonQ, PsiQuantum, Rigetti. Okay, but there are many others that are, building software. Like, so they're basically saying, well, we're going to create a quantum programming language. Okay, we are going to create a tool for optimizing the size of quantum circuits. Like you give us a quantum circuit and we'll try to reduce its depth to make it easier to run on a near-term device. Or they're saying, we will consult about quantum algorithms. So like you give us your application, we'll investigate what are the best quantum algorithms for that application. Okay. Or, we will provide an interface, a uniform interface to all different kinds of quantum computers. Okay, so there are a lot of companies that I think are sort of hoping to become the Microsoft of quantum computing. That sort of, they have some platform that everyone else has to go through. Okay, now from my perspective, all of this, it's as if people are sort of building up this tower, building up all the different layers of the tower. Okay, and yet, the bottom layer that it all rests on, the actual hardware, doesn't exist yet. Okay, so, this is the thing to understand about all of it, right? It's very hard to evaluate the tower before you sort of have seen the thing that it all rests on, right? And, you could say, personally, like, the progress that excites me the most is the, besides just purely theoretical stuff, right, would be, the progress that actually solidifies the base of this tower, right, that everyone else is going to have to build on. And, you could say, well, if you're doing something like designing a programming language, designing an interface, right, these are human problems as much as they are technical problems, right? Like a good programming language is one that will, spur, a thriving community of developers, right, who build on it and so on. But how do you know the answers to those questions before you have, the actual community of developers? And how do you get the community of developers before you have the actual devices, right? So it is, so there are these chicken and egg problems, right? And to be, in the quantum software space right now, to have a quantum software startup, means, for better or worse, it means sort of getting ahead of ourselves, right? It means, trying to build, these software tools for, for underlying platforms that don't really exist yet, or that, only exist in a very rudimentary form. That can be done, and it's possible that some of these quantum software startups will even be spectacularly successful, right? And maybe, one is very foolish not to invest in them, right? But it is sort of, it's not what I would regard as kind of the main technical problem that has to be solved in order to get from where we are to, a world with scalable quantum computers, right? I mean, I like some of these startups. I think they have good people, who are doing good things, and I'm happy if other people invest their money in them. Let's put it that way. Yeah. Okay. Mhm. All right. So quantum computing is a different way of exploiting nature to try to solve computational problems than anything that we've been doing in the past. It uses the rules of quantum mechanics to solve certain problems, certain specific problems, much faster than we know how to solve them with a classical computer. Okay, so the rules of quantum mechanics have been, at the core of physics since the 1920s, right? They've not changed in all that time. Okay, but it was only in the early 1980s that a few physicists started asking the sort of obvious in retrospect question of, what do those rules mean for computation? Okay, so, now the central things that quantum mechanics says, I won't really be able to do it justice in a minute or two, okay? But, it says that, the states of physical systems are sort of much bigger than it naively looks like, okay? You see like a system with, let's say n particles, and you think, well, that should take like, roughly n numbers to characterize the state of that system, right? Because I need to specify what each particle is doing. It's just like, which ones it's connected to, where is it in space, how fast is it moving, maybe some internal state that it has. Okay, quantum mechanics says no. To describe a general state of n particles, you actually need a list of something like 2 to the n power numbers. Okay, so in particular, if I have 1,000 particles, 2 to the 1,000 numbers is already far more numbers than could be written down in the whole observable universe. Okay, so that is an absolutely staggering claim, about the world. And again, physicists have known it for a century, right? Well, what's amazing is just that it took as long as it did for people to really take it seriously and say, what does it imply? But now the next really crucial thing to say is that you can't directly see these numbers. Okay, these numbers are called amplitudes. Amplitudes are related to probabilities, okay, but they're not probabilities. Okay, and for one thing, a probability that something happens is always a real number from 0 to 1. Right? You never talk about a negative 30% chance of rain. That would just be nonsense. Okay, amplitudes can be positive or negative. In fact, they can be complex numbers. Okay, so an amplitude is a complex number that you have to assign to each possible way that a physical system could evolve. So for example, if you have a computer with 1,000 bits in its memory, right, there are 2 to the 1,000 power possible configurations of those bits. Okay, and the rules of quantum mechanics say unequivocally that every one of those 2 to the 1,000 bit strings has to be assigned its own amplitude. Okay, but now, as I said, you don't directly see these amplitudes. Okay, there are kind of 2 things you can do to these, lists of amplitudes. You can apply linear transformations to them. Okay, this is called unitary transformations. And, for the last 100 years, the form that the laws of physics have taken has been, you specify the unitary transformation that these amplitudes undergo, right? All, I mean, with the exception of general relativity, basically all physics since that time, quantum field theory, the Standard Model, has all been just working out the details of what linear transformation gets applied to these amplitudes, okay? All within this framework of quantum mechanics. Okay, and then the second thing you can do is make a measurement. Okay, and famously, in quantum mechanics, measurement is treated as a very different kind of operation, right? It is a destructive operation where you force the system to randomly make up its mind about which outcome it wants to present to you, right? And then the central rule there is that the probability that you see a given outcome is the squared absolute value of the amplitude for that outcome. Okay, that's called the Born rule. That's one of the main rules of physics that we know. And whichever choice nature makes, like I might look at a qubit that has some amplitude to be, a qubit is just a quantum bit. So it would have the form like A0 plus B1. Like it has some amplitude A for being 0 and some other amplitude B for being 1, right? And now I can look at this qubit. I can ask it whether it's 0 or 1. If I do that, I will see 0 with probability the absolute value of A squared. And I will see 1 with probability absolute value of B squared. And whichever one I see, the qubit will then stick with that choice. Okay, so if it says 1 and I look again, then, and nothing's happened in between, then it's still 1. Okay, so again, I can make these linear transformations on my vector of size 2, my enormous vector of amplitudes of size 2 to the n. Those are completely deterministic. There's no randomness there. Those are reversible. Those are continuous. Or I can make a measurement, okay, which in practice means sort of I get the state of my quantum bits, my qubits, and I do something that records it on something much larger that I can actually look at and see, right? So it's no longer a microscopic state, but for example, a photon like goes into a photodetector and it either clicks or doesn't click, right? Depending on whether the photon was there. Okay, and now I no longer treat it as a superposition, right? Now I treat it as just a definite outcome, which has happened with some probability, which is the squared absolute value of the amplitude. Okay, so that was my attempt to explain quantum mechanics in 2 or 3 minutes. If you want the whole story, you should take a course. So I should say I do teach an undergrad course, quantum information science here, where we go through this. Brian LaCour also teaches actually a freshman course here at UT, and I'm glad that many other universities have courses on this stuff, which actually don't require much of anything in the way of physics background. Right? The main, I don't remember the course number. It's called Quantum Information Science. Okay. All right. Thank you. Yeah. So, the main prerequisites, for a course like that are linear algebra and complex numbers. Right? We actually don't have any physics prerequisite for this course. Yeah. Yeah. So, all right. To talk about the different quantum error correction techniques. Okay. So, the possibility of quantum error correction, of doing it at all, was very non-obvious, right? It was discovered by Peter Shor, same one from Shor's factoring algorithm in 1995. Okay, and what quantum error correction says basically is that it is possible to take a logical qubit, so like a superposition of the 0 state and the 1 state, that we are interested in. Okay, and the trouble is if I just try to store that in the state of a single electron, a single atom, something like that, it's very fragile. Okay, if any stray particle comes through and just carries away the information about whether that qubit was a 0 or a 1, then it is as if the qubit has been measured. Okay, so this is a really key point, right? From a modern perspective, all that measurement really means is that you yourself or your measuring device kind of becomes quantumly entangled with the qubit that you are looking at, right? Like the information from the qubit leaks into you, into the state of your computer, the state of your brain, the state of your environment. Okay, and but now anything else that had that same leaking effect, even if it's just some radiation in the room or something, right? If it carries away the information about whether the qubit was 0 or 1, then as far as you can tell, looking at the qubit, it will be exactly as if someone had come along and measured that qubit. Okay, and if someone measures the qubit, then it no longer has its superposition state, and so it is no longer useful to you for quantum computation, for sort of beating a classical computer. So what this means is that qubits have to be somehow very carefully protected from unwanted interaction with the environment. Okay, quantum error correction is the field that studies how to do that. Okay, and so it was initiated by Shor's discovery in 1995 that you can take a single qubit that you want to protect and you can encode it into an entangled state of 9, in his case, 9 physical qubits. Okay, in such a way that if any one of those 9 qubits was to leak its state into the environment, you can measure, you can realize that something bad happened, and you can perfectly recover the information that you cared about from the other 8 qubits. Okay, so that was the first example of a quantum error correcting code. Since then, people have discovered many, many, many more quantum error correcting codes, and there's a whole theory of quantum error correction now, mirroring the theory of classical error correction, that started with Claude Shannon in 1948. Okay, so we know a lot, about in principle now about how to do this. People are just now, beginning to demonstrate quantum error correction in the lab. And right now, it's still, you still have to squint to see whether there's any net win compared to if you hadn't done error correction at all, right? So it's still very marginal. Okay, but the hope is that once your qubits get good enough, at least what the theory says is that you pass a certain threshold, where then each round of error correction, once you're past this threshold, makes your qubits effectively better and better, makes them better and better protected. Okay, so that in the limit, you're just using noisy qubits, noisy physical qubits, in order to simulate effectively noiseless qubits. Right, and you might need thousands of noisy qubits to simulate just a single noiseless qubit. Okay, so there could be a very high overhead that you have to pay, but but the idea is you would just pay that, and then now we are not yet at the threshold where each round of this becomes a net win. You can say, like, we're not yet at the break-even point, or the critical point, if you want to think of it as as if it were a nuclear reaction. Okay, but that is the big goal today that I would say the different companies are closing in on. Now, you asked about different approaches, so I would say that if you want to make a division, the 2 main approaches would be software error correction and hardware error correction. Okay, so the underlying theoretical ideas are the same, or are very similar, but you can either just try to take a physical substrate like trapped ions or superconducting qubits that has kind of no natural error correction, and then you could try to build in the error correction at the software level, right? By just constantly measuring your physical qubits to see when errors have happened, and if they've happened, then you apply the appropriate correction operations. Okay, and this would be the analog of something that John von Neumann discovered in the 1950s. So, at that time, people were very worried that classical computers would never scale, because obviously you needed vacuum tubes or electromechanical relays to build them, but these were very unreliable components. Right? And as you integrate more and more of them, then the probability of a failure somewhere approaches 100%. So how do you do this, right? So John von Neumann. Okay, so yeah, so what? Yes. So von Neumann, who was one of the famous mathematicians and physicists of the 20th century, proved a theorem that said that as long as your rate of failure per vacuum tube is small enough, you can use noisy vacuum tubes to simulate noiseless ones, right? You can use error correcting codes. You can have sort of, layers upon layers of vacuum tubes that are basically checking each other's work, taking like best 2 out of 3, doing tricks like that. And as long as your physical error rate is small enough, you can effectively push it to 0. Now, as amazing as it was, von Neumann's great insight ended up mostly not being needed, okay, in the computing revolution. And why was that? Well, it was because by the 60s, we started building integrated circuits of transistors, and those almost never fail. Your laptop will maybe have a hardware failure about once per year when a cosmic ray hits it. Okay, if you have a data center the size of Google, then you actually are worried about cosmic rays, and but for most of us, we can just assume that our transistors are perfect. So it's natural to ask, well, couldn't we do something in quantum computing that was like that? Right? Instead of having to do all of this laborious error correction at the software level, analogous to what von Neumann said to do in the 50s, why couldn't we build qubits out of some physical substrate that was just sort of naturally robust against error, right? Like the transistor uses solid state physics to just sort of snap to, either on or off, like, current or no current, right? To sort of, take a continuous signal and snap it to something discrete. So why can't we have qubits that would sort of naturally be protected against decoherence? And there is a major proposal for how to do exactly that. That is topological quantum computing. Okay, that is the thing that is most associated with the physicist Alexei Kitaev, who came up with it in the I guess 1997 or so, and the idea is that if you could create, you would merely have to create a new type of material which has never been seen in nature, but it would have to support quasi particles. That is, like, it would have to have excitations on it that behave like particles, but neither like bosons nor like fermions. Right? Bosons and fermions are the two basic types of particle that make up our world. And they're each defined by the type of statistics that they satisfy. Like if I take, bosons or like, photons, for example, if I take two identical bosons and I swap them, then nothing happens. Okay, if I take, fermions are matter particles. Okay, quarks, electrons, neutrinos, these are all fermions. Okay, if I take two identical fermions and I swap them, then the amplitude for that state of the universe gets multiplied by -1. Okay, so, one consequence of this is that you could never have two fermions in the same place at the same time. That's called the Polyexclusion Principle. Okay, that's the reason for the stability of matter. That's why we don't all just collapse into nothing. Okay, bosons do not have the exclusion principle. Okay, and in fact, if you look at a laser, for example, that has tons and tons of photons in exactly the same quantum state. All right, so now the idea with topological quantum computing is you're going to create a new type of particle which cannot exist in 3 dimensions. It can only exist on a 2-dimensional surface. And they have statistics that are neither fermionic nor bosonic. But some complicated thing happens each time the paths of 2 of those particles go past each other. So each time they braid around each other. Okay, and the idea is that just the pattern of braiding of the paths taken by all of these particles, that will be what expresses your quantum computation. And now here's the key feature. Okay, here's the key reason people are interested. In order to cause an error in this quantum computation, it would not be enough to just slightly change the path of one of these particles. You would have to actually change the topology of how the particles are braided around each other. Like take 2 particles whose paths previously crossed and make them not cross, or something like that. Okay, so just the physics of your system gives you some intrinsic protection against error. Okay, and so that has been the dream for 20 plus years now, that we could just realize this topological matter and then have a substrate for quantum computing, which would be sort of naturally, physically error corrected, at least to some degree. Right, so that the need for software error correction would be a lot less. Okay, as I said, that's been the dream. So far, no one has managed to demonstrate a topological qubit. Okay, but if, whereas they have been able to demonstrate, ordinary qubits and have, actually, gotten, kind of impressively far with, scaling up to systems of 50 or 60 of them. Okay, but, this is why if someone manages to manufacture even 1 or 2 topological qubits that they can get to, interact with each other, apply a quantum gate to them, like that'll be a pretty big deal. Okay. Yeah. Okay, good. So the honest answer to that question is kind of a long one. It's an answer that takes like 3 lectures of my undergrad class, let's say. Okay, but I'll try to give you the short version. Okay, so currently, right, how do we protect our credit card numbers? When we order something over the internet, right? Well, we use one of the great inventions of computer science from the 1970s, what is called public key encryption. Right? We use methods of encryption where you and Amazon, or you and whoever you are buying, you're sending your credit card number to, do not have to have agreed on a secret key in advance. Right? That would make the whole thing very impractical. Right? Instead, let's say Amazon sends you a public key, okay, which you then use to encrypt your message, like your credit card number, but in such a way that it can only be decrypted, we think, by someone who has the private key. Okay, and the private key Amazon is keeping to itself. Okay, now the most popular forms of public key encryption, again, invented in the 70s, things like RSA. Okay, the Revesh Shamir Edelman form of encryption, where there the public key consists of a gigantic composite number. Okay, like a product of 2 enormous prime numbers. Okay, and the private key consists of the prime factors. Okay, so what Amazon does is it generates 2 enormous prime numbers, let's say with thousands of or at least hundreds of digits each, keeps those prime numbers secret, multiplies them together to get a composite number, which they then publish to the world. Okay, and then what RSA discovered was a way to take a message, encrypt it using the composite number in such a way that it seems to only be decryptable in any reasonable amount of time by somebody who knows the prime factors. Right? So we're relying on the belief here that multiplying 2 huge numbers is much, much harder than factoring the result back. Right? There seems to be an asymmetry between multiplying and factoring, which you might have encountered, even just in learning multiplication in grade school. Like, yeah, it seems harder to to factor a number, if I give it to you, than just multiply, factor 91 versus multiply 7 times 13, right? And indeed, the fastest classical methods that we know for factoring, there are some very clever methods known, but they still take time that roughly grows exponentially, right? Like, exponentially, actually, with the cube root of the number of digits of the prime numbers that you're looking for. Okay, but now, one thing that was clear from the beginning is that if anyone could discover a fast algorithm for factoring huge numbers, then that would break the entire system. Okay, now there are other cryptographic codes that we also use, like Diffie-Hellman, which also depend on other number theory problems, where you could tell a similar story, right? If anyone can find a fast algorithm to solve that number theory problem, then the whole crypto system is broken, is insecure, right? So it all depends, and this was the case all along, right? It all depends on this unproved belief about the hardness of a certain computational problem. Okay, now we can get to what was the famous discovery that really started the whole field of quantum computing, in 1994, right? That was when Peter Shor discovered his fast quantum algorithm for factoring numbers. Okay, so this was, this remains to this day the most famous quantum algorithm that anyone knows, or that's been discovered. It is what we call a polynomial time algorithm. So it's an algorithm that it uses a number of steps that grows basically like the number of digits in the number squared, roughly. Okay, as opposed to classically where we think you need an exponential number of steps, right? Or you do with any known method. Okay, so if you use Shor's algorithm, you could factor, let's say, a 2,000-digit number, right? Which someone was using for their public key in RSA, and you could thereby just break the whole system, right? You can then decrypt the message, as well as Amazon can. Okay, so now, how does Shor's algorithm work? That's the part where I was saying I would kind of need 3 lectures to give you an honest answer. Okay, but the important points that I would say to understand First of all, if you read almost any popular article about this subject, it will tell you something that sounds appealing and easy to remember and is totally wrong. Okay? It will say that, well, a quantum computer works by trying every possible answer in parallel. And so it's very simple how you break a cryptographic code. It just Shor's algorithm just tries every possible set of prime factors in superposition and then magically picks the best one. Okay, now the question you should ask yourself is, if it were that simple, then why would you have needed Peter Shor to think of it? Okay, so in fact, it's not that simple, right? I'll tell you what the problem is. Okay, if you just created an equal superposition over all the possible answers, right, and then you just looked at it, not having done anything else, then the rules of quantum mechanics, the ones that I talked about before, are completely unequivocal about what you're going to see. You're going to see a random answer. Okay, just a completely random answer. Okay, well now if all you wanted was a random answer, you could have saved a lot of trouble in building a quantum computer, right? You could have just flipped a coin instead of spending however many tens of billions of dollars to build this device, right? So the entire hope. This is really, really important. Okay, you can if you don't listen to anything else I say, right? The entire hope of getting an advantage from a quantum computer is to exploit the way that amplitudes, being complex numbers, work differently from probabilities. Okay, so like if I want to know the probability, of some, of my computer producing some output, like I might have to add up, probabilities of many, many different ways that output could have been arrived at, right? But all of those probabilities will be positive numbers, right? They'll all be from 0 to 1. Okay, the key thing in quantum mechanics is that if you want to know the amplitude for something to happen, right, now I have to add up the amplitudes for all of the different ways that it could have happened. And if some of those amplitudes are positive, for example, and if others are negative, then they can cancel each other out. Okay, which means that the total amplitude is 0, and which then means that thing never happens at all. Okay, that's called quantum interference. Right? Richard Feynman used to say that everything in quantum mechanics boils down to this one effect, over and over and over. Okay, so the amplitudes are complex numbers. Complex numbers can point in different directions and they can interfere. They can cancel each other out. Okay, so now the idea with every quantum algorithm, including Shor's factoring algorithm, right? The idea with every one of them is to somehow choreograph a pattern of interference, such that for each wrong answer, each answer that you don't want to see, some of the paths leading to that answer have positive amplitudes and others have negative amplitudes. So they interfere destructively and cancel each other out. Whereas for the right answer, the one you do want to see, you get constructive interference. Okay, all of the different paths leading to that have amplitudes that are reinforcing each other, that are all kind of pointing, in the same direction. If you can arrange that, then when you measure, you will see the right answer. And even if you did it less than perfectly, hopefully you'll see the right answer with a high probability, right? And then if you don't see it, you just repeat the algorithm from the beginning. Repeat several times. And like if each time I had a 10% chance of seeing the prime factors, then I've just got to run the whole algorithm like 10 times. And chances are that I'll have seen it, right? So that's, now the tricky part is that you have to arrange this whole interference pattern, even though you yourself don't know in advance which answer is the right one. Because if you knew that, then what would be the point? Right? You could just use a classical computer. Okay, and you have to do the whole thing faster than you could have just solved the problem with a classical computer. So the fact that there are any interesting quantum algorithms at all is kind of a miracle, right? It was not, when Feynman and Deutsch started talking about this in the early 80s, it was not obvious that a quantum computer would be good for anything other than just simulating quantum mechanics itself. Okay, so Shor's algorithm, is what helped change that, right? And gave people the idea that, wow, you can actually just take a problem like factoring that has nothing to do with quantum mechanics, and you can use quantum mechanics to solve it faster, right? Now, to explain how Shor's algorithm works, well, you first need some number theory, right? So there's just some stuff, that has nothing to do with quantum mechanics, but you have to reduce factoring to a different problem. Okay, you reduce it to a problem called finding the period of a periodic function. Okay, and then that still doesn't, it seems to be out of the frying pan into the fire, right? Seems like this problem is at least as hard as your original one, because you could have a function that repeats with some exponentially long period, and then how do I, just by accessing this function at different points, how do I figure out what the period is? Okay, so then what Shor says to do is create a quantum superposition over all possible inputs to this function, right? Evaluate it on superposition. So now you have all the possible outputs of the function. Okay, and now you're still not done, because now if I just look, then I would just see a random value of the function. Okay, but now what I do is an operation called the quantum Fourier transform. Okay, so I do a linear transformation on my list, my exponentially long list of amplitudes, that has the effect of taking my list of amplitudes and Fourier transforming it, for any of you who know what that means, right? Just changing the basis to the Fourier basis that then gives me enough information to see what was the period of my periodic function. Okay, so Shor had to show, that first of all, that this actually works, that you can piece together the result, and also that you could implement this quantum Fourier transform acting on an exponential vector of amplitudes with only like a linear or quadratic number of elementary operations of quantum gates. Okay, so that is all the stuff that I take 3 lectures to explain in my undergrad class. Okay, but the important takeaway points are that to make this work, Shor had to exploit some extremely special properties of the problem of factoring integers. Right? This is not just a general, you break any cryptographic code this way. Okay, and in fact, there are other cryptographic codes, including ones in widespread use, that we do not know how to break, even using a quantum computer. Okay, and there is a whole field today called post-quantum cryptography or quantum-resistant cryptography. Okay, that studies, how do you design cryptographic codes that will still be secure even in a world with quantum computers? And people have a lot of ideas about that. Okay, and the most natural reaction if someone builds a quantum computer should just be that we should all upgrade our web browsers and our web servers to use these post-quantum crypto systems. And NIST, National Institute of Standards and Technology, is trying to formulate standards right now for exactly those kinds of systems. It's just that for better or worse, what we use today on the internet is mostly systems that are not secure against quantum computers. Okay, RSA, Diffie-Hellman, elliptic curve cryptography, all of those could be broken, and migrating away from those, could be a big effort. And it might be that it'll be you'll have to drag people kicking and screaming to make that effort until they see that an actual quantum computer is imminent. Right, and then maybe they'll make the effort to upgrade all of their legacy code and their legacy hardware. All right. Yes. Yeah. All right. Sure. So so my field is computational complexity theory, that sort of studies the intrinsic difficulty of different problems. Maybe I should use the board. This marker doesn't work. Okay, so what we generally do is we sort of organize computational problems into classes, depending on what kinds of resources are able to solve those problems, right? So the most famous complexity classes are called P and NP. P being sort of all of the yes or no questions that are solvable by a conventional computer in a polynomial amount of time, meaning using a number of steps that scales at most like the size of the problem raised to some fixed power. Okay, so what are examples of problems in P? Okay, I give you a graph and I ask you, is it connected? Like, is every vertex reachable from every other vertex, right? I give you a number, I ask you whether it's prime or composite. That one, it is far from obvious that it's in P. That was only proven in 2002. Okay, but most of what we would do with our computers on a day-to-day basis, linear programming, to take an example, versions of multiplying, sorting, these are all polynomial time problems. Okay, now the next really important class is NP, which stands for non-deterministic polynomial time. Okay, and this is the class of all of the problems where it's slightly subtle, okay, but it's the class of all the problems where there is a polynomial time algorithm to check an alleged yes answer. Okay, so if someone claims to have solved it, then they can give you a witness that you then just check, and it's either right or it's wrong. Right? So factoring would be a good example, right? Like it might be very, very hard to find the prime factors of a 3,000 digit number. But if someone presents you, they say, here are the prime factors, then it's very, very easy to check them, or at least easy for your computer to check them, right? Because it multiplies them together. And as I said, there are even ways of checking that the numbers are prime. Okay, now, at the top of NP are the famous NP complete problems. Okay, and what it means for a problem to be NP complete is that you're in NP and you are maximally hard among all NP problems. Or in other words, like the NP complete problems are the problems in NP, sort of the easily checkable problems to which every other easily checkable problem can be easily reduced. Okay, so it's not obvious that there are any NP complete problems. Okay, the great discovery in the early 70s that sort of started theoretical computer science as a subject, was that there are, or computational complexity, was that not only are there NP complete problems, but sort of the great majority of the combinatorial search and optimization problems that we care about in practice are NP complete. Okay, so some famous examples would be the traveling salesperson problem, finding the shortest route that visits a collection of cities. Maximum clique, like find 500 people on Facebook who are all friends with one another. Given the dimensions of a bunch of boxes, can they be fit into the trunk of your car? Sudoku, Super Mario are actually known to be NP complete. So most problems involving kind of satisfying a whole bunch of constraints. And then there's this sort of intermediate zone, right? We think that there are, so okay, so you could say the great question of all of the greatest unsolved problem of computer science, of theoretical computer science anyway, is the question, does P equal NP? That is there a polynomial time algorithm to solve the NP problems? Which is equivalent to asking, is there a polynomial time algorithm to solve the NP complete problems? And if you discovered an algorithm for any one of them, then automatically it would imply algorithms for all of the rest. Okay, so that's the famous P versus NP problem that is one of the 7 problems of the millennium that has these $1 million prizes from the Clay Math Foundation. Okay, and then there is this weird stuff that seems to be in the middle. A famous example being factoring. Okay, factoring we don't know to be in P. That's why we use it for public key cryptography, because it seems to be hard. But we also don't know it to be NP complete. Okay, and in fact, factoring has extremely special structure that seems to prevent it from being NP complete. Okay, that structure was crucially exploited to design the RSA crypto system, that we all rely on to have, electronic commerce. But then, that same structure was also relied on by Peter Shor to give his quantum algorithm to solve factoring. Okay, so now the quantum generalization of P is this class that we call BQP, which stands for bounded error quantum polynomial time. Okay, and this is the think of it as the class of all the problems that are efficiently solvable by a quantum computer. Okay, so BQP contains classical P, right? Anything that a classical computer can do, a quantum computer can simulate. It contains at least one problem, factoring, which is not known to be, or believed to be in P. Now, crucially, we do not think that BQP contains all of NP. Okay, if there were a fast quantum algorithm for solving NP-complete problems, then that would really be revolutionary, right? That would that would change everything. And there was some early hope for that. And a lot of the popular articles will still just blithely write as if BQP contains NP, but we don't seem to live in that world. Then in the other direction, there might be BQP problems that are not even in NP. So there might be problems that a quantum computer can solve, but where a classical computer cannot even verify the answer efficiently, let alone finding it. Okay, and a good candidate for something like that would be problems that involve simulating quantum mechanics itself. Okay, so that's like there's again, I teach a whole graduate course called Quantum Complexity Theory, but this is the 5-minute version of kind of the most important actors in the drama, I would say. So I don't know if you want me to, yeah. All right, sure. Yeah. Well, okay. Well, I mean, at some point, I would like to write a survey article about, like a century of thought about why is quantum mechanics true, right? And I don't mean, yeah, and I don't mean, it's true because people did the experiments and they discovered that it was true, right? That's not an explanation. Kind of like why, just thinking a priori about the space of all physical theories. Why would you have, are there reasons why you would have expected quantum mechanics to be kind of a natural choice within that space, or even like, an overwhelmingly preferred choice? And I think, one can give some answers to that question, but, I'm not completely satisfied with them. And I just wanted to survey, what's been said about that. Yeah. Yeah, we got like 700 something comments. Yeah. Yeah, right. No, but also, a lot of people who are very, very confident that they know the answer. Obviously, quantum mechanics is true because X, except then, the next person has obviously it's true because Y, and, Y is different from X. So. Well, I'm not, I mean, there are a lot of things that I would like to pursue. Yeah, okay. All right, good. Okay, sure, yeah. Thanks for having me.
Get Denise set up.
This one. He's the one after. Which email? Do you want to just put it in there? Thank you. Sorry, he's running down the street. He's never on time.
Where do you guys have all the questions? They are coming up on Zoom, but we need to announce them. Yeah, it's kind of hard to straddle between the two. Yeah. So I pause at any given moment. Yeah. Okay, so kind of I saw some for Steve. Hopefully answer them by the end of my talk, but at the end of my talk, then we'll pause. Yeah. Here, I'll probably be raising my hand if there's going to be a question on Zoom. That'll be like the signal. So it's just this button? Yeah. Not that were sent to the PowerPoint. I got it. I'll share it. Yeah, should have just shared them.
Just came in for me, so hopefully it should be
Are doing well now that you've had some food in your tummies. I would like to go ahead and introduce our next speakers. Coming up next is going to be Denise Ruffner. She is the Chief Business Officer of Atom Computing, which is a startup credited with building the first quantum computer made of nuclear spin qubits. Denise has been involved in the industry since its inception, holding executive positions at IBM, IonQ, and Cambridge Quantum Computing. Denise is also the president and founder of Women in Quantum, which is a vibrant community supporting women's participation in the emerging QC industry. And joining Denise is going to be her colleague, Robin Cox, Vice President of Control Systems Engineering at Atom Computing, and she's also leading the development of Atom's very own control systems. Please welcome Denise and Robin to the stage.
Hey everyone, good afternoon. And I wanted to say thank you for including me to the group. And I also want to tell you how difficult it is to talk after Scott Aaronson. So I kind of want to like hide under this seat. But it's my pleasure to be here and want to talk probably a little bit about hardware and some more beginning ideas on hardware. But let's first start off with I think we just went through my history, so we don't have to talk too much, but been around in the quantum world for a while. Before that was doing high performance computing. I'm a biologist, I'm not a quantum scientist, so all technical questions go to my colleague Robin or to Scott. Maybe Robin, I'll have you introduce yourself real quickly next. Next slide.
Sure, I'm Robin Cox. I have a background originally in elementary particle physics. I worked on the CDF experiment at Fermilab as an undergrad and the Opal experiment at LEP, which was the predecessor to the LHC at CERN as a graduate student. And for the past 20 years or so, I've been involved in digital logic design primarily. I've worked on some space-based image processors, and I worked on telecom IP for RF transceivers at Analog Devices. And I was the R&D manager at National Instruments for the software-defined radio product line. And this does actually make sense because our control system at Atom Computing consists of RF devices that stimulate laser systems. So it's been a great path to kind of join Atom Computing and have the rest of the career path make sense and come back to the physics side of things as well. And I lead a team. We have a small office in Austin of the control systems team, hardware, software, and firmware engineers who are building the classical electronics that are orchestrating our quantum computer.
Thanks, Robin. So there is kind of a quantum computing hardware company in Austin. So wanted to bring that up. All right, let's go to the next slide. And what I wanted to do is talk a little bit contextually about high performance computing and quantum computing, get into commercial quantum computing, a little bit about the history of commercial quantum computing. You'll notice I asked Scott a question about benchmarking quantum computers. We can talk a little bit more about that. And then finally, Robin is going to talk about quantum computing, and then I'll end up talking about this group Women in Quantum that I started and mentoring opportunities that you all may want to take advantage of. And then also Steve from Strangeworks forwarded me some comments from the chat. And I'll also talk about job opportunities and some really good resources for you to have moving forward. So let's talk a little bit about high performance computing. Next slide. So when I started at IBM, or I started at IBM a long time ago, but I was involved in the sale of the Summit supercomputer at Oak Ridge National Labs. And this is a giant computer. It uses the energy equivalent to 10,000 homes. It's the size of 2 tennis courts, millions of miles of cables. Hey, Whurley, lots of $200 million. And it was like, of course, this computer could do anything that we ever thought it could do. It's so giant, right? And only to find out that actually there are a lot of problems that even Scott talked about that challenge these supercomputers. So there is a need for a new computing technology because not everything can be solved via classical computing. And even if you build a bigger and bigger supercomputer, you're not going to be able to solve a lot of problems. And so I just wanted to tell you, it also mentioned that a supercomputer like this is equivalent to a 50 to 60 qubit computer. Now that would be a fault tolerant computer. So we're not quite there yet today, but there's a lot of promise for quantum computing in terms of what the technology can bring to our world. If we go to the next slide, commercial quantum computing. So the first quantum computer, kind of commercial quantum computer, was put on the cloud by IBM in May of 2016. And this was a really small computer. It had 5 qubits. And at the time, we were very proud of it, which of course we should have been. And what was interesting is we were all like, should we put it on the cloud? Should we not? Are people going to care? Who's going to use it? Maybe a couple hundred people will use it. Kind of, we were like, let's just do this. And what happened is in the first week, over 7,000 people registered to use it, which blew us away. It wasn't what we expected. And if we look today, I looked at the IBM website, there's over 325,000 users running 2 billion circuits a day. So it's been quite a huge phenomenon. It's made quite an impact in the world that people can access a computer for free and use it. Now, there were a few other companies in May of 2016 that were also developing hardware. So many of you, I'm sure, have heard of Rigetti or Honeywell or IonQ, who were also introducing hardware. And at that time in 2016, there were about 10 companies that were already developing software for quantum computers. So Scott mentioned earlier that there's, and I'll come up to numbers of companies, but you can see that this is an industry that's still very early. So the first computer comes out in 2016. It's 6 years later, and the industry is just still growing. So I encourage all of you to stay interested in this industry because there's so much going on and there's so much in the future that if you're thinking about what should I do in my life, this is really a great industry. All right, next slide. What's interesting, and Scott again referred to this, is I'm going to show you a couple different slides. There's 144 groups developing quantum hardware. This is a table from the Quantum Computing Report, which you guys can subscribe to as students very inexpensively. And it's always a great summary of what's happening in the quantum computing world. But you can see across the top that there are a number of different modalities of quantum computers. So we don't really know what the winning modality is. So there's a lot of companies and academic labs that are all trying to develop computers and what we each think is the best modality, but we don't really know. And you can see just the names of some of the companies here. If we go to the next slide, I've kind of shown this information in 3 different ways just to give you an impact. But you can see starting in 2018, you can see the number of hardware companies is growing. So we had 30 in 2018, and now we have about 60 in 2021, 2022. The technologies we've seen on the market are superconducting, which I'm sure you're all familiar with IBM, with Google, Rigetti. Trapped ion has come out, and IonQ, Honeywell, or Quantinuum, as well as AQT out of Austria. We believe that the next technology that's going to come out is the neutral atom technology. And that's part of the reason why Robin is here today to talk about what atom computing is doing. And I do want to say we do have publications on everything we've done. That was kind of, this is not a PowerPoint presentation. But I want you also to see that there are other modalities for quantum computing. And I've listed companies underneath them, and there's more companies than that. So the race is still on, and we don't know who the winner is. If you guys watch Twitter, there's a channel called the Quantum Bullshit Detector, which is one of my favorite channels. And whoever that person is says this is a horse race, and we don't know which is a horse and which is a mule. And I love that perspective because we all do think we're right, and we all do think we're very committed to what we're doing. But there's a lot of engineering challenges in every modality, and we'll see what happens as this moves forward. I like the next slide, and I just put it up because I thought it was a good illustration. This is by a guy named Michel Cursec out of France, where on the wheel you can see the different modalities, and then kind of the spokes at the edge show all the different companies or universities developing the technology. So right now, there's a lot of interest in hardware. There's a lot of interest in hardware development. It's countries doing it. It's academic labs. It's companies. A lot of activity. All right, let's go to the next slide. This is a point I really wanted to underscore, and that is there's a tendency to say, I have 5 qubits and you have 4, so my machine is better. And that's not true. And so at IBM, very early on, we realized that there has to be some way to express how good your quantum computer is. And so we put together a metric, and it's on the next slide, that we call the quantum volume. Bam. All right. And quantum volume was our first pass at how to benchmark a quantum computer. So that if I look at the Atom Computing quantum computer versus another brand quantum computer, there might be some standard way we could measure how each computer performs and compare them. Now, what's happened is, since quantum volume was suggested, well, I'll mention right now the most highest quantum volume today is at Honeywell or Quantinuum. But since this metric was introduced, there's been a lot of discussion of, is this the right metric? What other factors did we miss in this metric? What else should we be doing? And so for that reason, go to the next slide. I asked Scott a loaded question. IBM has introduced a new metric called CLOPS, where they look at compute time and they bring that into the equation. That may be one way to evaluate it. Atos has come up with something called Q-score. Quantum Economic Development Consortium has also come up with a benchmark. And DARPA has awarded 3 different grants to try to create new benchmarks. So I think what we can see is, again, we're still working on technologies, but we're also still working on benchmarks and how we're going to compare system to system. And so I just want you to see that there's a bigger picture out there on really how you evaluate a system. And what's interesting is we talk about numbers of qubits, but if you go back a slide, other way, yeah, you can see that right now the world record is on a 12-qubit device. So there's a lot of people that we have 100 qubits, IBM has 100 plus qubits. It's really the quality of the qubits that matters. So someone can win with 12 qubits versus these other places that have much larger numbers of qubits. Okay. So there's a term in quantum computing called quantum advantage. And that is, can you show an example of where a quantum computer exceeds the capabilities of a high-performance computer? And there's really been one instance that I think of when people ask me for examples of, has anybody ever done this? And this was done actually in 2019 by Google. It was a very smart, well thought out experiment. They did a calculation in less than 4 minutes that they say the world's most powerful computer would have taken 10,000 years to perform. So that second half of it is subject to a little bit of negotiation. Well, but there is, yeah. So there's some advantage. The tail end is debatable, and there were immediately some papers published on that. But there was some advantage shown, and to me, it was just a positive indication for quantum computing as opposed to a real big milestone. All right. I just wanted to show you there's a huge quantum ecosystem out there. There's startups worldwide. I've broken out startups by country. This includes hardware and software startups. Obviously, there's a lot in the US, but there's startups in Uruguay, there's startups in India, there's startups in Singapore, all over the world. So this is a phenomena that's really taking off, and it's really great to see that it's spread all over the world. What's very interesting is that countries are really starting to get into the quantum computing race. And there is quite a bit of funding available. in many countries. And probably the country that does the largest amount of funding for quantum computing is China. So China is outspending us. Right now, it's around $11 billion. The second country, or the second biggest country investment in quantum computing right now is in Germany. Angelica Merkel was actually, or is a quantum physicist. And that's something she felt very strongly about, that this technology could really affect the economy of the country, and really wanted to invest very deeply in it. And I think over time, we're going to see larger and larger investments by countries all over the world in quantum computing. I do want to mention that the public markets, so now we have quantum computing companies that are public. This is something new. I'm going to talk about hardware companies. So if we go to the next slide, Archer has been public probably for a couple years. It's a small company in Australia that converted from a mining company to a quantum computing company. But what's very interesting, last year, IonQ went public through a SPAC, and we can talk about what a SPAC means, and Rigetti went public this year. So what that means is, for me, is that investors in the world are starting to recognize that this is a technology, and the technology has promise, and they're willing to invest money into this. So it's a great, again, a great recognition of the market, and it shows to me that there's going to be some stability in the market moving forward, and that people are interested, and it's going to grow. All right, so if we look at the quantum industry journey, we started out, let's say in 2005, I'm going to say when IBM put their system on the cloud, that systems, quantum computers can be built, which is pretty exciting in itself. Next, we're looking at systems with a path to error correction, and then scaling systems, and then finally exploring applications and watching applications proliferate. So we still have a long ways to go in the journey, especially around error correction, but it's a very good journey, and there's a lot of really great work being done by a lot of different places. All right. So now I'm going to have Robin talk a little bit about atom computing and what we're doing to give you a flavor of a startup's version.
Sure. So atom computing was founded in 2018 in Berkeley, California by Ben Bloom and Jonathan King. And Ben Bloom did his graduate research in atomic clocks, and this will make, hence the name atom computing. We're making our quantum computer from optically trapped neutral atoms. And so it started with 2 people in 2018, and now this picture was taken about a year ago, and now we're almost at 50. So we hired a lot of people during the pandemic. So next slide, please. So yes, Atom was founded in 2018. We, in July of this last year, we announced our 100-qubit quantum computer called Phoenix, which is located in our facility in Berkeley. And we're essentially creating qubits from optically trapped strontium atoms. So strontium, so we're taking a beam of strontium atoms, and we're using a series of lasers to cool them down, because it's a block of strontium in an oven, and so the atoms kind of fly off this block of strontium because you heat it up. But in order to actually create a quantum computer, you need to trap the atoms into an array. So we use lasers for all of this. And so we have succeeded in creating our 100-qubit system. And one of the advantages of using neutral atoms is they stick around. When you create a qubit from a neutral atom, it sticks around for a long time. So this is the so-called coherence time, which is effectively the time you can use the qubit to perform computations. And compared to some of the other techniques, our qubits persist for tens of seconds. We actually have recently had a paper accepted by Nature Communications where we are demonstrating our 40-second coherence time. In contrast, some of the other techniques are orders of magnitude less time that they're coherent. So the operations take place faster, but they don't persist for as long. In January of this year, we announced our Series B fundraising. So we raised $6 million for a total funding of $80 million, and we're growing quite rapidly. We are primarily hiring both physicists, primarily atomic physicists, and people who are specializing in quantum information, as well as my team on the control systems team. We hire more classically trained engineers like hardware engineers, firmware engineers, software engineers. So even if you're not a quantum physicist, there is still definitely a place for you in the quantum computing industry. There's a lot of talk about amongst people in quantum computing companies that there's going to be a workforce shortage. So even if any one company doesn't succeed, there's going to be plenty of job opportunities in the other companies for people who have domain-specific engineering knowledge in quantum computing. So next slide, please. So what is neutral atom quantum computing? Well, atom computing, I really like our company name because it basically describes what we do. We're creating a computer based on atoms. So we're using individual alkaline earth atoms that are trapped in a 2D array. And one of the advantages of using neutral atoms is they're intrinsically identical. Some of the other techniques like superconducting transmon qubits rely on fabricating semiconductor devices, and there are kind of systematic uncertainties for each of the, the elements that is creating each qubit, but we don't have to deal with that with neutral atoms because all the atoms are by definition the same. We are also operating our device at room temperature, so we don't have to worry about huge roomfuls of cryogenic refrigeration electronics, and we don't have to have our electronics in a cryo environment. So and one of the advantages on the control system side is we can actually individually address the atoms, but we don't need individual channels for each qubit. We can, with one channel of electronics, address an entire row in our array. So it makes the control system a lot simpler. All of the atoms and qubits are controlled by lasers, so we're taking advantage of decades of experimental developments in atomic physics. So that's why we hire a lot of atomic physicists, because they're setting up the lasers and the optics that are necessary to cool the qubits, create optical traps so we can have individual atoms and arrays. And then we're also using lasers to manipulate the atoms into the atomic states necessary to create 1 and 2 qubit gates. So yes, I basically gone through this. So the initial step in our experimental sequences are we prepare the atoms. So there's a hot stream of atoms that's cooled and trapped with lasers. And then we have a group of people who are working on creating series of algorithms from the top level, from the computer science, theoretical computer science algorithm, all the way down the stack to how to translating the algorithm into quantum gates, translating those quantum gates into hardware instructions. And then my team, we're kind of at the bottom where we're taking those hardware instructions and we're manipulating a series of lasers using custom RF pulses. So we're very concerned with controlling very precisely the amplitude, frequency, and phase of RF pulses. And then another part of the control system is we actually do our readout by taking high precision scientific imagers. So we're doing some real-time image processing to detect the atoms in a specific state. So we have this very clever technique where, so when we do a readout, and the qubit is either in a 0 or 1 state. And so what we do, we use this technique called shelving, where qubits that are in the 0 state, we kind of give them a kick with a laser into a state where they just kind of hang out. And the ones in the 1 state, we give another kick, and then they emit a photon that can be detected by the camera. So you can see in your array which of the qubits is a 1 state. And then the control systems group is controlling the scientific imager and running some real-time DSP and a field programmable gate array to determine whether or not there are atoms in those particular spots. So next slide, please. Yeah, so as far as what's important for a quantum computer, of course, the number of qubits. but also we want to make sure that we can either minimize the sources of uncertainty and error in our qubits, because in a quantum computer, errors can kind of collapse the quantum state and then mess up your calculation. So we want to be able to either correct for the errors that we do have and minimize the ones that we can control. I mentioned coherence time, which is effectively the amount of time that we can do quantum computations, and the more precise control over the lasers we have and the less noise in the laser system, the better off we are. We also need to control magnetic fields, because we use magnetic fields to split the atomic energy states. So we need, one of the other functions that my team is working on is a way to very precisely servo the magnetic field, and when we measure it's a little off, we kind of do a closed loop control to get it back to where we want it to be. And of course, faster gates mean faster computations, and so the way we achieve that in the atom computing system is through better vacuum systems, and we are actually considering using cryogenics. We don't have to, but we can. So next slide. Okay, yes, I alluded to our kind of flagship quantum computer, which we're calling Phoenix, which is located in Berkeley, and it is a 100-qubit system. And this photo is mostly optics for the laser systems. We have a whole bunch of lasers that we need to kind of steer. There's a very complex sequence of laser operations at specific times in order to slow down the atoms so that we can trap them, create the traps, make sure that the array is fully filled. There's when we fill the array, typically only half of the sites are full, so we have some atoms in reserve that we use a series of RF pulses to kind of kick the spare atoms into the array so it's fully populated. And then we can start our quantum computations with yet another series of lasers to create the quantum bits. So right now we consider Phoenix basically our first generation system, and we're in the process of building our second generation systems, which are multiple systems that we're building in Boulder, Colorado. And we're targeting approximately 1,000 qubits for those, and we're aiming for commercial availability early next year. And then it's on to larger numbers of qubits with improved fidelity and improved error correction capability. And now I'm going to turn it back over to Denise to talk about women in quantum, which we both are. So
didn't even think about
that.
Okay. So let's pause for a minute. Any questions on quantum computing hardware ecosystem, neutral atom, quantum computing?
Okay. So my question was, like, I guess, how do you actually calculate like what to do with the lasers in order to to the atom and then measure that? Because like with photons and stuff, it's like you like linear algebra, like you have the matrices and you can like calculate it. But it's like, what's the actual, I guess, process of like knowing what gates to apply with the lasers and like how it goes to each?
Yeah, so we have an entire team of atomic physicists who have created our so-called gate schemes. So basically, it's I'm like the wrong person to ask about like exactly. So essentially, we've defined a series of in order to create the qubits, you need to put the strontium or the other alkaline earth elements into excited states, and then they have the correct kind of physical characteristics of a qubit, and then so people are computing what wavelength of light you need to excite these atoms in these specific states, and then it's up to my team to actually, they say, okay, we want to put the atom from the ground state to the like minus 9/2 excited state, right? So then that translates to my team, and you have to give it a kick of 100 megahertz RF pulse to something that controls the laser so that it gives that atom that kick. But as far as the actual details of the gate schemes, it's probably will take longer than we have here, and I'm probably not the right person. But if you look in our preprint that just came out, there's a nice diagram that describes exactly like how we make our 1 qubit gates. So I can refer you to that. So yeah.
Good cue. Thank you. All right. I just wanted to talk for a minute about a group we have called Women in Quantum. This is a worldwide group with about 9,000 people in it. And we've had to date 4 virtual summits, a couple in-person summits. We do annual awards. We do scholarships where we send people to go to scientific meetings or trade shows. So it's just a really great group I want you to all be aware of. We use this group as a way to highlight women's contributions in quantum computing, but everybody's welcome to come. So all you guys are welcome to come. We'd love to include you. I want to go to the next slide and talk real quickly. What we have is a mentoring program. So this is something that we started offering 6 or 9 months ago. Next slide. And it's sponsored by a company called Keysight Technologies. And essentially what's happened is we have people all around the world that have signed up to be mentors and signed up to be mentees. And we have some very accomplished people as mentors like Will Oliver from MIT or Jay Lowell from Boeing, the head of applications, Ann Matsuura at Intel. So we have this wonderful group of mentors. And what we do is as you sign up, we match you with mentors and we give you the opportunity to spend 30 to 60 minutes with them every month and get their advice, whether it's on what's your next career step, whether it's science, whatever it is. We try very hard to match you with people of like interests. And it's just a great program open to everyone for free. So if you want to take advantage of it, we literally match every Friday. So you have time before the next match if you want to join us. Finally, I want to talk, there is a newsletter, and I don't have the URL on here, but I can share it with Nathan. Oak Ridge National Labs shares a newsletter that you open it up and it looks like it just has like industry news. And then you page down and you page down and you page down. And they list conferences, jobs. They list, for example, 92 new quantum jobs last week. They list every single one of them. There's 1,245 current jobs open. They list every single one of them. It is the best go-to resource to look for internships, to look for postdocs, for faculty positions. It's all in one place. It's free, comes out every Sunday morning. So for those of you that I saw in the chat that were asking questions on what are the jobs, what do I need to get a job, this is a really great one-stop place to go to check out jobs. And also to learn more what people are looking for. It's really great to read. All right, wanted to say thank you. And if there's any other questions, I'm hoping I'm finished on time. So thank you very much for listening, everyone.
I'll hand this off to you in a minute. Enabling anyone in the world with an internet connection to learn about and leverage this game-changing technology. In addition to Strangeworks, Whurley has founded Chaotic Moon Studios, Honest Dollar, Ecliptic Capital, and philanthropic efforts including CERN's Entrepreneurship Student Program and Equals, the gender partnership for gender equality in the digital age. So everyone, please give a warm welcome to Whurley.
Thank you. Okay, so first, fair warning. I'm just now showing up because we're always back to back to back, and I will be leaving you as soon as I'm done. So if anyone online or in the audience wants to find me, I'm just at Whurley everywhere, Twitter, Facebook, everywhere. And my email is just Whurley, WHURLEY at strangeworks.com. So I'm going to go through this a little fast because I was hoping to hold for questions at the end. I'm here to talk to you about the software side of the house, but I don't know what questions you have. So I didn't want to make a super generic presentation. So I was talking to Nathan about giving an overview of kind of the industry, where it's at, who the players are, all that good stuff. We'll get through all of that. But I really want to know who in here, show of hands right now, wants to work in quantum computing that knew that before they came in the room. I would like resumes from all of you and anyone online that's holding up their hand, which is awkward because they're probably by themselves. So let's get started. Oops, sorry. Maybe we'll get started. There we go. We can just do that. So the first thing I want to do is talk about software. And so I love software. I'm not on the hardware side. I'm not a physicist. I don't know enough about any of that. But software is like my favorite thing in the world because software has one mission and one mission only, and that's to eliminate complexity. And the reason we started a company in quantum computing was kind of threefold. One, we sold our last company to Goldman Sachs in a 1-year anniversary, and while that was really great and fun, it was also like we didn't really get to build everything we wanted to build. Two, we wanted a big field that had a long, future. So didn't want to get in something on the tail end, wanted to get something on the very beginning. I think Scott set expectations appropriately, as did Denise. We're in the very early days. I mean, it's amazing. And three, quantum has a lot of complexity. And in that complexity, there's a lot of opportunity to apply software, whether it be down in the firmware level or the control systems, to noise control, all the way up through the stack to the user interfaces and abstraction layers. There is a ton of opportunity. And what's awesome about being here on campus or when I'm on any campus is that all of you are living in the greatest time to be alive in the history of the world. When I went to start stuff technologically, I would have to cut UPC codes out of serial boxes and then go to a physical email box where I'd drop it in and wait 12 weeks to get something. You guys can fire up an Amazon cluster more powerful than most corporations had 10 years ago, about 30 minutes. You have access to free computers through Strangeworks, through IBM, through everything. So it's an incredible time to be alive and be around this. And so let's talk about what the industry looks like and then specifics on the software industry. How many of you have been following quantum for more than a year? Why did you not raise your hand saying you wanted a job in quantum? Are you just lurking? Because I counted all the hands first time, and then I counted all the hands there. There were 7 of you that didn't raise your hand. So look at you specifically. I'm just kidding. So when we first started, we started as a Linux Foundation project. The idea was that I would leave Goldman, and this would be one big open source set of software. But due to a bunch of reasons, we started, it kind of looked like this. There was no software. There was all hardware investment. And there was software being used, but there weren't really any software companies. And around the same time, QCware and Zapata and ourselves and a few others kind of became like some of the early software companies. And that led to this today. So there's now over 229 startups worldwide that we watch and try to monitor as best we can. There were 3 primary technologies for building these machines. There are now 9 that we interoperate with. There were no publicly traded companies. There's now 3, about to be 4 at the end of summer. $20 billion invested by governments all around the world. Those 37 master degree programs, there were only 4 when we started. So this is a lot of change for 3 years. We just turned 4 in March, and I'm astounded at the level and the pace with which things are accelerating in the space. That doesn't mean, I think Scott would agree, that this is, you're going to make billions next year in it. I mean, this is still a very long-term game, but that's a super exciting place to be in, a super exciting place to be in the industry. So, whoops, sorry about that. So where exactly are we? Well, when we started, it was hard to figure out where to start. That's gotten a little bit easier. There were a bunch of companies, so it was really easy to get confused. And that's primarily about kind of the news. So as you've seen, some people in companies say, we've just made this huge quantum breakthrough. And then some professors at certain universities write blog posts, maybe not. And so there's a lot of confusion. If you're an enterprise customer or if you're wanting to get into quantum, it's hard to know sometimes where to get your information. For example, there's several reports that there was $421 million spent in quantum last year. I'm here to promise you there was not. That is incorrect at best. That doesn't mean it's not the most exciting space in computer science to be in. It just means, we need to be a little factual with that. But the news was confusing, then it's still confusing. Then getting the rug pulled out from under you has gotten a little better. But it used to be you'd be using a framework, it would get updated. What would happen? Your stuff would break, you'd have to go redo it. It's getting a little better, but interoperability between frameworks, still not great. Everybody wants to be the one, just like the hardware side. Using more than one frameworks almost all the time when you're working with these. So it's really important to be able to tie all of that stuff together. The most important thing is the pricing model. Until Rigetti went on Amazon, it could be millions of dollars, or you could use it for free. But many of the people offering the machines for free had a user license agreement that said anything you ran on the machine, they could patent. So not free. So that's changed a lot. And Amazon has taken that down to, I think Rigetti's still around 30 cents a shot. So there's plenty of options, free options, people looking for people to test, stuff that you can pay cheap. There's no reason not be playing with these machines today. And there's plenty of machines to play with. The thing that gets me excited is quantum investment. Now, there's still not a lot of software investment, okay? But there's a ton of opportunity. And if we look at it, we can look at it this way. 2015 through 2021, venture investment was total about $1.4 billion. And you can kind of see 2017, which is where we started looking at forming, there was a little bit of an uptick, right? It dropped back down in 2018. That's when we got our funding around January. And then now, look at that. I mean, 2020 was a hell of a year, right? Not so much. In 2021 alone, there was 3.2 billion invested in quantum companies. Okay, now this includes SPACs and venture investment and private equity investment, but a billion of that rather was all in the last 3 months of the year. So think about that, 1.4 billion from 2015 until 2020, 3.2 billion the next year. So we doubled the amount of investment in quantum technologies and startups not from a government standpoint. We're not talking about the billions, tens of billions governments are putting in. We're just talking about people trying to make money on a hot quantum startup. Okay, that went from 1.4 billion from 2015 to 2020 to 2.2 billion in the first 3 quarters and $1 billion in the second. That is quite a pace of investment, which either means this is going to be hot or there's a whole lot of Quibi and Theranos on that chart. But I don't know. We'll see. You guys do follow business news, right? Just double checking. Just so you know, everybody in the audience thought that was hilarious. That's online. I know what your problem is. So let's talk about the players for a little bit. And again, I'm going to rocket through this so we get some questions. All of these people are playing, and all of them are doing interesting things, including the hardware companies listed on here, in software. So when I wanted to talk about software, I don't want to just talk about, you know, what Blue Cat's doing in Japan or 1Qubit up in Canada or us or anybody. There's software up and down and all around the stack. And there are a ton of opportunities. Opportunities to write compilers, cross compilers, opportunities to write control systems. It goes on and on and on and on. There is a green field if you want to write software for you to write software for quantum computers. Everything that we have today is great. It's nowhere near what we need to have, and it will change so much between now and a general purpose quantum computer that it'll look like a completely different industry, almost, in my opinion. So what are some examples of what people are doing with quantum software? Well, as and what was your name all the way in the back that showed me the picture of me? Yes. Jess? Okay, so Jess was like, hey, is this you? Embarrassing. It's a picture of me at South by with Mayor Pete apparently wearing the exact same thing I'm wearing today. So she showed me the picture. I was like, oh, shit. But the reason I was talking to Mayor Pete is one of the first areas that could be quantum, although there's chemistry and all these things, is actually transportation industry. And not just because, you know, of logistics and routes, but also because of new chemistry for concrete and asphalt and things that are more environmentally friendly, right? Tons of reasons. So I wanted to share what some people are doing, and then I wanted to jump into Q&As and make sure we answer any of your software questions directly. And that should, if I do this, put us through right about on time. So Volkswagen, they're doing some really cool stuff. So's BMW. A lot of the German auto manufacturers, Audi, working on stuff too, are doing really, really cool stuff. Volkswagen, particularly, has been working on what? Traffic management, optimization. You know, quantum is pretty decent at that. It's not bad. Airbus is not just using quantum computing. They're using quantum computing. They're using sensors. They're using communications to build all of their next-gen technologies. So this, you know, it brings up an interesting question, which is, you know, quantum software is not just quantum computing, right? It's software for taking in sensor data or pre-processing sensor data. It's software for managing telecommunications over, you know, entangled networks, et cetera, et cetera. So all of the opportunity I talked about a moment ago was just in the computing side. There are what you might consider two whole other industries in kind of quantum information systems that are now burgeoning that might provide even more opportunities for software. Sorry, I'm so hoarse. MasterCard, they're doing customer experience work. This is really interesting. I've been approached by, since we started the company, by tons of ad and media companies wanting to know how they could crunch data to better identify customers and do all of that. It's an interesting play. It's also popular in loyalty programs where they're looking at, you know, how do they figure out either probability of people buying stuff, probability of people accepting offers, things like that. Probably not what I would use quantum computing for. I like the environment, the chemistry, and the material science and stuff, but you know, still valid. Speaking of the environment, Total has been using it to create new algorithms for their CO2 capture, which is super cool. I think the environment is one of the biggest opportunities for quantum computing, hands down. And that's not just this environment, but you know, Cyber Rodeo was Thursday. We were out there, and great, we want to go to Mars. Well, there's also a lot of environmental problems there. So I think these new computers are the key to our future. What I mean by that, it won't just be quantum. There'll be amorphic, neuromorphic, DNA, maybe plant-based stuff one day. But if you think about it, there was an industrial age that revolutionized the world, and then there was an information age that did that again. I think now we're looking at the quantum age. I think quantum sensing and networking and computing are going to be what builds trillions of dollars worth of value in markets in the future. So I think it's super, super important to be looking at the long-term view on this. I mean, you shouldn't have a 2-3 year view of, hey, I'm going to get out of school. What am I going to do? You should have a 10, 20, 30 year view of how you're going to make your mark on history, because while I'm too old for that, everyone in this room has a chance, except for Steve and me. And Toshiba, we talked about communications. They've got a really great software doing a quantum key distribution. Quantinuum, likewise, has quantum keys that were generated on a quantum computer that you can get through an API service. Tons of stuff happening right now today. AT&T, telecommunications networks. They have to figure out what's next, right? Because what does SpaceX do? They're not a space company. They're a telecommunications company. That's why they're launching thousands of satellites. They're going to put AT&T and Comcast and everybody out of business. So they're looking at what's next. Well, what's next for telecommunications? Quantum communications, right? Quantum networks. So the last thing I want to talk about, I want to rocket through this really fast, and then I want to get to a few Q&As. I brought some books, so we'll get to that in a minute, is why Austin? Now, I know this is being broadcast online. It's not just here. I understand that Austin is not the center of the universe, and I really wish everybody would stop moving here. But it looks like I could be wrong, because it does look a little bit like it. So one of my goals is I would like to make Austin one of the centers of quantum computing. Now, when I say that, understand that every quantum computing company, including us, has employees all over the world. There are maybe 200 or 300 people still that matter in quantum worldwide, that really matter. Maybe 2,500, 3,000 if you were just crazy and counted every employee and whatever. There are going to be hundreds of thousands of jobs in quantum information science and in quantum computing easily. Okay, and so I want us to make a mark here in Austin, but like I said, that doesn't mean everybody's going to be here. It does mean if you ever come to work for us and you're out on the internet there, you get to come and visit Austin, which is super cool. And I like it because, again, you don't move here and then you go back. So it's great. But this is just some of the stuff that's happening here right now. 1,800 new hires from Samsung, 25 for Oracle, 15,000 Apple is going to go to, 5,000 for Tesla. It's amazing. There's gravity. And the reason I bring this up is because centers of gravity matter. It's valuable to Silicon Valley. It's valuable to Austin in the next phase of technology, meaning that companies here, I think, will have an advantage in working with some of the companies up there. Because I think interpersonal communication, even though we live in the world of Zoom, is really important. I travel all over the world to try to meet our clients and friends around. And when I say we want to make it Austin, we want to kind of take all of the building connections and the talent we have here and the quantum ecosystem and kind of tie them all together. Again, people won't move here to work for me. Some people will. Not everybody will. Some people can't. I have engineers in Minneapolis. I have engineers in Dusseldorf, Germany. We have people everywhere. And that's kind of what you're thinking the company compositions will look like. So we built the ecosystem. I'm not going to talk about it a lot, but if you want to go play, you can go to quantumcomputing.com. And there's a simple code library, a web-based IDE, and some hardware to look at. And the thing I want to end with before we go to Q&A and giving away some books here is we're hiring, which is something everybody's asked us for 3 years. And we said, no, we're not hiring. So if you are interested, you can go to strangeworks.com, /resume, okay, /resume, and just start filling out an application. We'd love to talk to you because we're definitely recruiting. We're definitely recruiting very heavy. And we're definitely recruiting worldwide. Now, you may live in a geography where we're not set up to do business. That's not a problem. We've set geographies up to hire the right talent. So if you're the right talent and you're out there, don't worry about moving to Austin or where you're at. We're willing to talk to you. And like I said, it's a global market and global competition. So software questions. We have 5 minutes, maybe a little more. You can't raise your hand that early. What'd you say? Were you verified? Oh, okay. He's got, and I was going to say, if you're online, Steve is here. And he is, I think, posted, if you'll put your questions online, he will refer them to me. If you're online and it's a really good question, you are not getting a book today, but you can email me if you wrote down the email address later, and I will send you one. You had a question first. We'll do his, and then you're online and go back. Yes, sir.
All right, so my question is regarding the thoughts on potentially building operating systems for quantum computers in the future, whether that be text-based, graphical.
Give me that microphone. Operating systems. I'm just messing with you. The problem with operating systems, you hit my pet peeve. We don't even have RAM for these computers, right? There's not even a form of memory. So please continue, but know that this answer is going to be like in 30 years, all right?
I think. I guess I think I'm good now.
Look, when people say they're building operating systems today, which is, by the way, a great question, my least favorite question, but you're going to get a book just because that is baller. And I didn't mean to like shell shock you or anything, but most of what they're talking about is system on a chip, right? Which is not quite operating system. When I met with a company last year, and there's like 12 of them. They're like, we're building a quantum OS. I'm like, for what computer? And they're like, for all of them. It's like, that's not how any of them work. And I worked on the operating system team at Apple way, way back in the day. There were like thousands of people that worked on that. And it took years and years and years. I have to imagine this quantum thing is going to be significantly more complicated for that. Steve, what's the online question? Then we'll come back to the room. Well, I mean, I think that's everything. I think abstraction layers are desperately needed. I see a couple different problems. One, if we had a 1,000,000 qubit machine today, we dropped it into Austin or London or Tokyo or New York or wherever, I don't know which one of us would program it. I think it might be infinitely more complex than we think. I don't think it's simple as we did 10 gates, now we do 1,000,000 gates. There's a very specific approaches to solving problems here. I think user interface is what takes us from physicists to developers, and eventually from developers to subject matter experts, and eventually to just anybody that's an enthusiast that wants to play around with the tech. I think this is super, super important that we have these interfaces, that we have these abstraction layers. And I also think the interoperability between the machines, between the frameworks, all of that is something that we could definitely do a better job on. I'll come right back to you. I'm going to go to you, sir, since you asked. Did you have a question too? I'll go to you too. The tech part. Yeah, yes. So the question was, what came first for you, the personal part or the technical part? Right? Is that fair? The technical part. I used to be horrible and not like talking in front of people or anything. So that's part's all developed, as has the tech some. Although I'm kind of rusty now, for sure. Did you, Steve, have any more online before we kick one out, and then we'll come back to you? I think it was you, and then we'll come to you. Well, challenge number one, we're writing software for computers that don't exist really, so that's always difficult. I say that because a lot of these machines are more great lab equipment for exploring the quantum landscape than computers, and I don't say that with any offense to any of my hardware friends. I say that because the decoherence times are still so short and the circuit times are still so long that a lot of times the machine isn't viable by the time you run a circuit. And we have a long way to go. For me, when we get to a general purpose quantum computer, we'll be there because then I can, at any time I want, call the one and it will process it and at some point give me an answer back. But these aren't like, a Dell 1U box. These are very complicated systems. And the people working on the hardware are extremely bright and talented. And it's taking a long time because it is groundbreaking science. It's super cool. But, we had honestly, we've had a couple of problems. One, it's been hard to be a software company in a hardware world for 3 years where we're saying we're building software for all of these users, and people are like, but the machine doesn't work, right? So that's been a little hard to get people like, yeah, we know, but it's going to take a long time for us to build this, and we think there's going to be a point where we intercept that market. Two, it's been hard finding people to get feedback from. There's not a lot of people in quantum computing. And there's not a lot of people that can give you really valid feedback from the software side or the physics side, right? Our joke when we started was software engineers aren't really that great at physics and physicists aren't that great at software engineering. It's like, I wrote quantum computing for babies. Doesn't make me Einstein or Schrodinger. You're a physicist and downloaded something off of GitHub. You're not a software engineer, right? We need to work together. We want to bring those two worlds together. And that was hard in the beginning when we were outsiders, but now it's gotten considerably easier as the pace of everything's picked up as well. You were next, and don't worry, I won't forget you. Yes, sir. That's a great question. Those industries, I think, will be primarily software driven. I don't know. I think, when I think of it, I think, there's a guy at IBM that has made quantum music, and there's people that have done, the computer and stuff. When I think of a valuable technology, I think a lot of it in industries that are creative will be used, not seen. So an example, your mom or grandma might use text messaging and autocorrect. And well, that will get eventually better, right, with a predictive probabilistic technology of what you're trying to do. Well, think about you're trying to quantize a song that you're mastering, or you're trying to move stuff. All of these things might, come into play. I have heard people say there'd be a desktop computer in 5 years. I don't know that I'm on that bus, but I think that when you think about creative technologies, it'll be things that you take advantage of that you don't see behind the scenes for now. More importantly, what the future brings, I don't know. There's a guy that I'm helping in Miami who has a crazy ambitious music and art project where he thinks that, you can use an algorithm to predict mood, and you come into the room and the whole thing is basically like almost a holodeck kind of thing. I don't know about any of that. I mean, for right now, these machines are really for very, very specific problems. They're not going to make the cat video on the internet faster. They are going to make a new material science for, cars and planes and spaceships or whatever. That doesn't mean that they won't, but quantum computing is not an island to itself. It's really, really important to understand that this technology integrates with other technologies. You can't use a quantum computer today without the classical side. Most people running stuff are running classical to quantum and back, right? And that will expand and get more complex. So, in a dream world, I would love to see quantum everything, right? But I don't know how much those industries will be affected on the you using quantum versus say you're searching through a catalog of music, and they can have, Google's applied Grover search algorithm and has a discography, and now you can search more efficient and find what you're looking for the new mix or whatever. That's what I say when I say you'll be affected by it, but not necessarily directly using it in those kind of things. Let's go to. I didn't mention who it was, other than Miami. Sorry, because NDA and stuff. But there's some cool stuff going on. Let's go to you because you had a question.
I guess you briefly covered it, but how do you expect to continue developing the software if the appropriate hardware doesn't exist? And how do you continue that development? And I guess also how in the future would you plan to integrate the hardware with the software when the hardware is not properly functioning to meet the software developing needs?
So the question for the people online is around how do you develop software like when we started 3 years ago when the computers kind of really aren't there? And it depends on the software you're developing, right? Obviously, for years and years now, we've needed control systems and pulse control and things like that. So, there's been software development. When we say software, we do mean what that other question online was. We mean more general, user interfaces and integrations of different things, et cetera, et cetera. But look, it's been difficult, but now it's gotten easier because now there's 229 companies, not 12, and there's a lot of progress. The hardware has progressed. Think about this. Fifth Solvit Conference, 1927, thought of quantum. 1980, Feynman and Benioff, let's use a block sphere basically as a bit, right? Fast forward to 2012, MIT has 12 qubits, okay? 2017, we went from 12 to 15 to 17 to 60 to hundreds. You heard Denise's machine earlier. I think you said the 100 qubits out now, right, Denise? Right? IBM has 127. You have others, and this is the danger, the warning. Qubit number irrelevant, right? Because 5,000 qubits on an Euler is not like 100 qubits on Denise's machine is not like 127 on IBM's, right? These all mean different things, but as it's progressed, it's got considerably easier. Now, you had a question. Okay, you have a question. You were next, so I'm going to go to you, and then to Steve, and then to you, and then to you. I think that's everybody, right? Nobody over there, and then you. Yes, sorry. Go ahead.
I know Strangeworks offers support for different languages like Qiskit or SDKs like Qiskit and Q#. Can you say, or are you allowed to say which one has been the easiest to integrate from Strangeworks side or from the user side?
No, man, they're like the little Lebowski urban achievers. Proud we are of all of them. No, I'm not going to pick a favorite. They've all been stupidly hard to integrate. That's the reality. But good question. Steve, got anything from online? So right now with the platform, you can go to quantumcomputing.com, use pretty much a ton of the frameworks on a ton of targets, simulators, emulators, machines. Our original goal was humanizing quantum, which was to make it, again, out of the hands of the physicist, into the hands of developers, eventually out of the hands of developers, in the hands of everybody. I mean, think about it. 20 years ago, when you were in college, not taking CS, you probably didn't code. Now you're building websites and doing stuff and everything. We want to drive it. That's why we were quantum computing for babies. We want to drive this. I do believe this, not AI, is the space race of our generation. And it is vitally important that we get it distributed as widely as possible, that we have as much open knowledge as possible. And that's kind of what the platform started as and about. Now we've advanced that a lot since then, but the whole focus is still making sure that we make it very easy for companies and people that want to adopt quantum computing to be able to get into it and get up and running with it fast and get benefits from it as well. I think it was you, sir, that I said I was going to go to next after him.
And CERT from Google.
Yeah.
Some of the other things that we use, Penny Lane, Strawberry Fields, but I'm wondering where academia is gravitating towards, because I know I spend probably half my time just setting up my local box just to get it to work with the simulator.
Well, sounds like you need Strangeworks. But no, seriously, the question for online was, where do I see academia leaning? He was saying he uses CERC, he uses Qiskit, etc. I think that so prevailing wisdom would tell you that the hardware and the software will be consolidated, right, over time. That's true if we're at the point where there was an actual industry. We're pre that point. We're not in the time of AMD versus Intel. We're in the time of like vacuum tubes, versus little electrical gates or whatever. It's still early on. Now it's moving super fast. And if you got involved today and it hit in 3 years or 5 years, you would still probably potentially be behind, right? Like it's going. But as far as academia, I think that, what I see most popular is definitely Qiskit. IBM is a huge university program. Denise was probably partially responsible for that, I think, and getting it to all the universities. But Qiskit, CERC, Forest, I see Ticket, I see a number of the frameworks. It depends on what you're trying to do and the research you're trying to do. Some of these are better for some things than they are for others, just like the machines. So, where does it go? I don't know, but I don't think you're going to see that consolidation for a while. I think you're going to see a proliferation of new hardware types. We went from kind of 3 to 9. I think there's going to be even more. Nick Farina in Chicago, for example, using helium electrons. The topological qubits, the silicon spin stuff. None of that was really going, last year or the year before in any like, hey, we're going to do a thing. And still could be some of those a year or two away. But that's going to mean more frameworks to deal with those. And so I think it's going to expand more. So I see academia having to figure out how do they build coursework around maybe the top 2 or 3 or something, moving forward. Now, where did he go with the mic? He's right there. I'm going to go to your question. Yes, ma'am. But he's bringing you a mic, I think. And then since you're right there, we'll go to
Hello?
you when she gets my mic. Go for it.
Okay, so I've never used a quantum computer before, and I've never accessed one. So what do commands look like for a quantum computer? Like Python?
Okay. Yeah, but it's flashing red, the battery warning light. Okay, so to answer your question, it looks like a lot of Python right now, right, for the most part. So it's Python language. You're usually instantiating, either entanglement or teleportation or something. It depends on what you're doing. So like Shor's algorithm, for example, is super simple, most of it. And then there's one step we're trying to order the number of what is in that key you're trying to decrypt. But when you're calling it, I think this is part of the limitation of quantum, is that right now it still requires, in the early days of computing, you had to be an electrical engineer to understand the flow of electricity between the gates to program a machine. Today, you need to have some physics knowledge. It's extremely hard still to do anything significant without having that physics knowledge. And so right now, I would say I don't think it's daunting, depending on your experience with programming and stuff, but I think that, it's almost all Python in the frameworks you're using. It's all calls that you're calling to stuff that you can't really go further than. So for example, in Microsoft's format, you can call a teleportation call, but if you go, if it breaks on you, there's, you're sending stuff to these machines. Already you're seeing that get easier. So for example, IBM has introduced runtimes. So they're taking the circuits that have been designed that you would normally set up on your machine and do the calls and putting them resident on the quantum computer so that you're just doing an API call to it. And I would be willing to bet that in the next 16 months, the majority of what you'll see will be you making an API call, calling an actual function. So maybe it's a variational quantum eigensolver, or maybe it's a QAOA or something like that. But you'll be more working with the data set and setting the parameters and making that call as opposed to writing that software yourself.
Okay, wait, like quick follow up here. So,
Sure.
so are these calls like measurements? Like are these kind of like the commands we're talking about?
Yeah, you could measure things, but like the variational quantum eigensolver measures the minimum Hamiltonian value, eigenvalue of a Hamiltonian, right? So there's all, I mean, it's literally the same. You're just calling a different machine. It's all, I think Python again is going to be dominant. I think when you look at it, I don't think you're going to get a chance. I hope you don't get a chance to go into the low level programming unless you're doing controls and like, for example, if you're using open pulse. So you're then making calls to basically change the pulse of the microwaves on the IBM machine, right? I think that that's fascinating stuff. I don't think 99% of people who have data and have a purpose for using quantum would know about microwave pulses. So I think you're going to see this be a world where it's a lot of API calls. It's going to look a lot like Rust. It's going to look a lot like when you set up an AWS service, right? You're going to say, I need to orchestrate something between these machines, and there's already wrappers for that, and you'll just call the wrapper, and then you do an API call and tie in your data. That's not exciting, but that's where it needs to go to get adopted. Because if we depend on where it is current state for quantum computing to take off as an industry, we are a couple million people and 20 years behind it being usable, right? We're going to have to advance it to make it as easy to use as when you're deploying a web server or deploying other services. So that's what my hope is. And so I'm trying to put the kibosh on, all the multiple languages and all the frameworks. I think it should be more managed services and API calls, because I think that's the majority of users are not physicists and they're not even software developers. We can see there's, out of those 313,000 people, Denise, is that the number you said? I think 313,000 you said? 325,000, even more, I was off. If you think about those 325,000 people, how many do you think would be physicists, Denise? 7, 20, 30? It's really, there's a big delta between what you do now and like where I'm hoping to take things and where we're hoping as a team to take things in just the next few short years. I'm gone over, but that's okay. I know he's gonna be the last question, and I'm gonna pass a couple of these out. I'll get it to you. Go ahead. What was your
I
question?
just had a small question about something on the slide. So you mentioned
Which slide?
You mentioned MasterCard and Airbus are all trying to use quantum technologies.
Uh-huh.
So given the fact that none of these machines are actually practical for doing almost anything useful.
Still practical for building intellectual property and running experiments on.
I see. Okay. Okay.
Sorry, I get that question a lot.
Right.
And the question was, given the machines aren't really at a stable state to be doing massive calculations and stuff on, why are these companies wasting any time with it? And it's because these companies see it coming. They're building IP around it. Some of them are trying to patent algorithms. I don't think you should do that, but that's, to each their own. But they're building intellectual property. They're building programs, training people on how to use machines, answering the questions she asked. How do I program it? What calls am I making? What's going on? And by the way, that shifts depending on where you're at in the stack and what tools you're using. But that's why they're using them, because Airbus, Volkswagen, all of these companies, they see a change coming, that kind of quantum age that I talked about. And if they're not already there and don't already have a team and have the knowledge, then they're going to be left way, way behind. And so you see a lot of the companies that think pretty far in advance have already been playing with this for years. BMW is a great example. In fact, they're one of the organizations behind the Munich Quantum Center. Munich Quantum Valley, right, Steve? That's what they call it. Yeah, Munich Quantum Valley. You got to stop saying the center. All right, well, I apologize, but I went 10 minutes over what I thought it would. Okay, one more question in back. Go for it. We're bringing you a mic. This is going to have to be the last one, though.
What are your opinions on what a potential quantum architecture would look like?
For software or for hardware?
Hardware.
I have no idea. I'm not in hardware. Sorry. Look, I think right now what you see is a lot of bump bonding, right? So between the quantum chip and the classical compute side of it, I think the architectures, like I said, we had 3 when we started. There were more, but there weren't anybody really working and funding. Now there's 9. I think there'll be 16, 18, 20. There's a bunch of ways to work with these particles, and everybody has a different way, whether it's silicon spin or ion traps or superconducting or annealing or whatever. And I think you're going to see more. The architectures fascinate me, even though that's nowhere near my area of expertise. But I really, really think that there's not going to be a consolidation. And I don't know 2 things about hardware architecture. One, I don't think all hardware will be good for all quantum computing challenges. I think some things will be better at some things, and some things will be better at other things. And 2, I think the more proliferation of hardware we could have right now is actually better, as long as we can get the abstraction layers to have as many people as possible playing with it and giving it feedback. Because one of the things I think that's held back the hardware side is, there hasn't been a lot of software interest. And so how are you going to get it to a user and test it? Steve came up with a wonderful program called Backstage Pass, where you apply and you get access to hardware early, and you get to give them the feedback, and you get vetted and stuff. That loop has kind of been missing. There's an argument to say it hasn't, because there's obviously software people I know that were working in quantum years ago, which is how I got inspired to get into it. But the hardware architectures, I think they look dramatically different in the future than they do now. Do what? Gibson. His phone number is 512. His wife's phone number is 512. But this is really important note on the hardware architectures and like where is it all going. That's why I think all of you should be involved in quantum right now today, is you could be driving where that architecture is going. You know what I mean? This is amazing ground floor opportunity. I think that superconducting and ion traps will kind of rule the day. I think the annealers will fade away eventually. Not fade away, be gone, but like Fujitsu and Hitachi have digital annealers and emulators that are almost as good as their own machines, but they're a fraction of the cost. So clearly they have a cost advantage, right? I mean, one of the big things with hardware is return on investment. If you're gonna try to buy a machine, it's tens of millions of dollars. Nobody in the enterprise is gonna do that anytime soon. I mean, maybe in a rounding error on a government sale or something, okay? But we need to get the cost and access free or cheap. We need to get the educational resources much, much lower in our education system globally, but especially here in the US. And then we need to focus on, what are we actually doing to drive a return on investment? I think that is the number one key question for all of quantum is, great, I'm going to spend $25 million with you, and then I'm going to spend millions of dollars setting up a team and do all this stuff. How does it actually improve my business? How do I get a return? And that sucks because it's such a capitalist thing to say. But the fact is I'm not going to be able to sell any software if I can't tell them that. And you're certainly not going to be able to sell them any hardware. But again, it is a ground floor opportunity. I mean, yeah, there's a ton of companies formed already. There's a ton of stuff going on. None of us are guaranteed to be successful, guys. None of us. We could be out of business in a month. We could be ruling the world. So could 229 other companies I told you about, right? Or 100 new companies that'll form this year that we don't even know. Maybe it's your hardware company. This is an incredible opportunity to get involved at the ground floor of this technology. And I would urge you to not pass it by. Again, I'm Whurley everywhere. We're 20 minutes over now. Thank you for all the questions. So thank you very much. You guys have a great day.
Oh, no. Yeah, you can go ahead. So that pretty much ends the whole event. I think there might be pizza arriving very shortly if you guys want to stick around. We also highly recommend you guys socialize with the speakers, chat with them if they're available to stay. We have some other members from Strangeworks here to talk to, even though I think Whurley has to go. Denise is still there in the back, and so is, yes, Robin's right there. Yes. So yeah, feel free to, mix and mingle, and thank you all for coming. Have a wonderful rest of the day. Yes, I did mention the pizza's coming, yes.